So let's get started with the calculations and solution of problem 2.7. What to do. So let's just start from one end, A. We want to find the expected value of x. So what is the expected value of x? Where from our reading of the exercise text, we know that x is a uniformly distributed random variable with density 1 over b, with b being positive and with the density defined on the interval 0 to b, hence integrating to the total of 1. Okay, so what is the mean of x? Let us try to look at this. So by the definition we wrote up earlier, the mean of x is given by this expression here, which we may find in the book. And as we noted earlier, it is well defined in our case, since 1, x is non-negative, so it would be well defined even if the mean was infinite. And 2, it is in fact not infinite, since x is bounded because the density is only positive on a finite interval. So the mean of x is given by the integral of x multiplied by the density, integrated on minus infinity to infinity. So plugging in the density, since the density is only positive on 0 to b, we can replace our bounds with 0 to b, and then I have x 1 over b dx. And this gives me the antiderivative of x is a half x squared. You may check that by your own calculations. And we evaluate it in b minus the expression evaluated in 0. And this gives me b squared divided by 2b, which is just equal to b halves. Now let's follow up with a little bit of intuition here. Why do I say that? Well, intuition. We can ask ourselves, is this result unexpected? And then we can say, well, it's not a surprising result, since x can obtain any value between 0 and b with equal probability. The value between 0 and b completely randomly, so with equal probability. And what can we see from that? Well, hence a best guess could just as well be the value in the middle. Now this is very, very vague, but I still think it's good to have this kind of intuition discussion just to round off an exercise, also because it's kind of a mnemonic device to help you remember, oh, what's the mean of a uniform random variable? Well, that's just the midpoint of whatever interval it's defined on. Well, that's a good way to remember things. Yeah, so that was the mean of x. Now let's take a look at the next part, B, where we are asked to find the mean excess. So it's the mean of the excess, given that x is greater than some value. So the mean of x minus d, given that x is greater than d, where we assume that d lies between 0 and b. So let us just start out by writing that instead. Have a little bit of rigorousness in here. So assume d belongs somewhere between 0 and b. Now I could have written 0 is strictly smaller than d, which is strictly smaller than b, but the reason why I like to write this instead is because then I actually know that my statement concerns d as a focus. If I write this thing over here, the statement could just as well have been meant for b I could have meant let b be greater than d, where d is something that's positive. But no, actually what I actually want to say here is we want to assume that d lies between 0 and b, where d stands for, in the non-life insurance case, a deductible. And in this sense, well, it only makes sense if we assume d is between 0 and b, if we want to find the mean of how much greater x is compared to d. So assume that d lies between 0 and b. And then the mean of x minus d, given that x is greater than d, is given by, and according to the formula on page 18, it is given by this. And I know that this is actually not what's in the formula on page 18. What's on the formula on page 18 is vaguely different from this, but notation-wise. But I just wanted to show you guys this notation because it's good to have. So what is on the formula on page 18 is in fact this. On the formula on page 18, the numerator is given by the mean of x minus of x minus d in this case, and in this case it would be multiplied by the indicator of x being greater than d. It would look like this, right? So this is what's actually on page 18, and these two expressions in the numerator, they're just two sides of exactly the same coin. They are notation for exactly the same thing, and we call this the mean of x minus d restricted to x greater than d. So this thing here, we may think of it as a and, or we may also think of it as a restricted to an event. So restricted to. And the reason why we call this the mean of x minus d restricted to x greater than d is because of the definition of it. It is the mean of x minus d multiplied by the indicator of the event that x is greater than d. And if we were to calculate that, if we were to calculate that, so just the numerator for now, this is equal to the mean of this thing over here, which is the integral of x minus d multiplied by the indicator that x is greater than d, and then of course multiplied by the density, since we're calculating the mean of this expression, and over the entire real line. Then afterwards we can take the indicator and plug it into the bounds. So we want x to be greater than d, which means we integrate from d all the way up to infinity. Then I have x minus d f of x dx. And now let's plug in the density. What is the density in our case? In our case, the density f of x, let's recall that it is equal to 1 over b, right? If x lies between 0 and b, and it's 0 otherwise. So what does this mean? This means that the density is 0 for all values greater than b. And we also recall that we have assumed that b is greater than d, so this works out pretty nicely. We integrate from d to b over x minus d multiplied by 1 over b. Now we can do a bit more tricking here because, well, we integrate x minus d from d to b, right? That is the same as integrating x from, well, 0 up to b minus d. So here we do integration by substitution. As soon as you get used to this, this won't look mysterious at all. If you're not used to this, do the calculations for yourself. Get used to integration by substitution. You can do it, I'm sure. Okay, and then I have that this is given by, all in all, 1 over b multiplied by 1/2 multiplied by b minus d squared. So this is the value of the numerator. Now, what about the denominator then? So now I have the numerator. Now I want the denominator, the probability that x is greater than d. Well, for any event that we want to find the probability of, we can find that event by integrating the density over the set that the event is given by. So we want to integrate the density over d to infinity, and then we recall that the density is bounded by b. So I have 1 over b dx, just like this. So the probability that x is greater than d is just given by the length of the interval I'm integrating on, because 1 over b is a constant, right? Like this. All in all, that gives me, according to my formula, that the mean, so let's just write up the conclusion in a nice purple here. So the mean of x minus d, given that x is greater than d, is given by this expression divided by this expression. So what I can see is a b disappears, and a b disappears, a b minus d disappears, and a b minus d disappears. So this is all in all equal to b minus d halves. And that was the solution of part B. And do we find this surprising? Well, frankly, no. And the reason why we do not find this surprising, frankly, is because, again, given the knowledge that x exceeds d, we know that x can live somewhere between b and d, right? Now, any value between b and d, x can take with equal probability because x is uniformly distributed. So given that we know that x is greater than d, what can we expect x? So how much greater than d can we expect x to be? Well, it's somewhere between 0 and b minus d greater than d. And any of those values, x can take with uniform probability. So hence we just choose the middle point, in a sense. So intuitively, this makes sense as well. So we're running out of time on this video, so for part C, please see the next video.